Let us take the third type of utility function, which is perfect complementary utility function. We will learn how the consumer chooses its optimal bundle when he maximizes his utility. Okay, so first, what is the general form? So general form for this kind of utility function is, that is, let us suppose utility derived from the good x and y is equal to, which is equal to minimum of ax by. This is the general form. So utility derived from good x and y is equal to minimum of whatever is in the parenthesis, that is a times x comma b times y. X and y denote the goods, a and b are the constants here. Okay, so this perfect complementary utility function, we also call this Leontief utility. We also call it fixed proportion utility function. So our endeavor is to find out the consumer optimization. That means we want to maximize the utility of the consumer, which is equal to minimum of a times x comma b times y. And this consumer will be facing some budget constraint. Let us draw here, subject to the constraint, that is price of x times units of x plus price of good y times units of good y should be equal to the income of the consumer. Okay, so we want to maximize the utility subject to this budget constraint. Now what happens in case of fixed proportion utility function or Leontief utility function? Consumer consumes goods in a fixed proportion. Okay, so a simple example that we give is that, let us suppose a person goes to a shop and he buys a pair of shoes. Okay, so we are talking about a rational, or rather a healthy person who has two legs. Obviously we are not taking the case of the specially abled person, so we are taking the general case where a person has two legs. Okay, so when he goes to the shop, he purchases a pair of shoes, so left shoe and right shoe. Okay, so by purchasing this, let us suppose this consumer gets a utility of, let us say, 12. Now if this person chooses two left shoes and only one right shoe, again his utility will be same, because this extra left shoe will not give him additional utility. And in the same logic, if he chooses one left shoe and two right shoe, in this case also his utility will be constant, same what he was getting from one left shoe and one right shoe. But if he increases left shoe by 2, that means if he doubles the left shoe and doubles the right shoe, in this case his utility will change to, let us say, 24. So consumer's utility will only change when he increases the consumption of goods in a fixed proportion. That means if he doubles the units of good L, he has to double the units of good R to get more utility. Changing only one good without changing the another good will not yield any additional utility. That is the main essence of the Leontief utility function. Okay, so having said that, where will the consumer achieve its equilibrium? Okay, so for equilibrium or at equilibrium, what we do, we equate whatever is in our utility function in the parenthesis. That is, at equilibrium, consumer will choose ax is equal to b times y. Okay, so this condition must hold at equilibrium. Solving for y, So y will be equal to a upon b x. Okay, graphically it is by, if I draw a simple graph here, we have x on the horizontal axis, y on the vertical axis. So at equilibrium, what happens? The equilibrium bundle will lie where y is equal to a upon b x. That means this very line denotes ax is equal to by. Ax is equal to by. Okay, so our optimal bundle will lie at that very point. Now to find out the demand function or optimal bundle for good x and y, so let us draw the budget constraint also here first. So let us suppose this is our budget line. Now at equilibrium, what happens? We plug y is equal to a upon bx into the budget line. So we have price of x times x plus price of y times the value of y is a upon bx is equal to m. So let's take x common. We will be left with px plus a py upon b is equal to m. Solving further, so it becomes b times px plus a times py upon b is equal to m. Okay, so I am getting out of the limits here, so let me be within the limits. Okay, solving further, so x will be equal to, x is equal to, transpose it here, it becomes b times m divided by b px plus a p y. Let us divide numerator and denominator by b. So x will be equal to, so b upon b is 1, so we are left with m. Here b upon b is 1, we are left with px. So here it will become a upon b, p times y. This is the optimal bundle of good, optimal choice of good x. Likewise, to find out the optimal choice of good y, what will we do? We plug y is equal to this stuff, or rather x is equal to this stuff in this equation. So y will be equal to a upon b, the value of x is m divided by px plus a upon by times the price of y, good y. So y will be equal to, so it becomes am divided by, so b into px, so we have b into px plus here b and b will get cancelled, we are left with a times py. Divide both sides by a, y star will be equal to m divided by b upon a times px plus a and a gets cancelled, we are left with py. This is the optimal choice of good x. Now in this case, our indifference curves will be L-shaped, and our, let us say this is IC2. So the point where budget line and indifference curve, which is L-shaped in case of perfectly complementary utility function, optimal choice we will get an interior solution. So here we get x star, y star. Okay, now why it is L-shaped, we will also discuss about that. Now we know that our optimal choice will lie at this dotted line. Below this, what happens? Ax is greater than by, and here ax is less than by. Okay, so this below this dotted line is the region where ax is greater than by. Above this dotted region, ax is less than by. So here you can see, if we are at this point, let us say x star, and we are getting y star as the optimal choice. If I increase x, okay, without changing y, my utility will not increase, because we have to choose the bundles in a fixed proportion. If I increase x by, if I multiply x by 2, I have to multiply y by 2. So let me explain it here. So we have x and y here, and let us say we have this indifference curve. Let us suppose it gives us utility of 10, and at this point let us suppose we are consuming, we have okay, let me write here L and R to explain it in case of left shoe and the right shoe. So let us suppose here we have 1, L is equal to 1, R is equal to 1. So we are getting utility as 10 at this point. Now if I increase left shoe to 2 at this point, but I am not increasing right shoe, again I will be on the same point, my utility will not increase. Likewise, if I increase it to 3, I am still at this at this line. So because it is L-shaped, utility will remain same. Similarly, if I increase R to, let us suppose 2, without changing L, I will be again on this L-shaped line. So my utility will not change at all. Okay. So to understand it better, I will take a specific utility function here and solve it. Okay. So let us take a specific example. So let us say utility derived from two goods x and y is equal to minimum of x comma 2y. Okay. We have the budget for that. Let us suppose price of good x is 1, price of good y is equal to 2, and income of the consumer is 12. So we want to maximize the utility subject to the budget constraint, that is price of x times units of good x plus price of y times units of good y should be equal to the income of the consumer. Specifically px is 1, so we have x plus py is 2, so we have 2 times y should be equal to 12. Okay, so at equilibrium what happens? At equilibrium x is equal to 2y, so we equate whatever is in the parenthesis in the utility function. So then we plug x equal to 2y in this equation, so we have 2y plus 2y is equal to 12. 4y is equal to 12 implies y is equal to 3. So y is equal to 3, which means x will be equal to 6. So x is equal to 6. So we have optimal bundle is 6 comma 3, or let me write it here, x star y star is equal to 6 3. This is our optimal bundle. Now how do we show it on the graph? Let me draw a simple graph here. So we have good x on the horizontal axis, good y on the vertical axis. X is equal to 2y, so it will look like this. Okay, so this is our x is equal to 2y. This is our ray where our optimal bundle will lie. So we have a budget constraint, that is x plus 2y is equal to 12. If I draw it here, so when y is equal to 0, x is equal to 12. Let us suppose here it is 12, and when x is equal to 0, y will be equal to 12 upon 2, which is 6. Let us suppose it is here. So when I join, this is our budget line. Okay, now we got at this point our indifference curve which touches the budget line. So at this point we are getting 6 units of good x and 3 units of good y, which maximizes our utility. And let us see here whether it is true or not. So we have utility is a function of good x and y, which is equal to minimum of x comma 2y. Now let us see what is the utility derived. So when x is equal to 6, y is equal to 3, so we have minimum of x is 3, or rather x is 6, 2 times y is 3, so we are getting 6 is the utility here. Okay, u is equal to 6. Now if I increase x to 7, so let us suppose I increase x to from 6 to 7, so what will be our utility? So u will be equal to 7 3, which is minimum of, we have 7 times 2 into 3 again, so the minimum of 2 into 3 is 6 and 7 is again 6. So if I change it to 7, still I am getting a utility of 6. Likewise, if I increase, so I take these 6, the units of x. If I increase units of y from 3 to 4, so let us see. So we have minimum of x is 6, so we have 2 into y is 4 this time. So here you can see minimum of 6 and 8 is again 6. So I am at this point. Let us suppose it is 4. Again I am on the same indifference curve. Okay, so my utility does not increase. So consumer will always choose to consume at this kink point. Okay, that's why we are calling it a fixed proportion utility function, where a consumer consumes goods in a fixed proportion. We also call this Leontief utility function. So that's it.